Okay, students, we're going to go through starting with chapter 15, number 23. We're going to go through all the problems in the textbook that I said would be important for what we're going to do next week. And I said it'd be on Monday, but we'll make it Tuesday. So, first, number 23, canceled flights. Mary is deciding whether to book the cheaper flight home from college after her final exams. The wording here is a little tricky. It says she thinks there's only a 20% chance that the exam will be scheduled after the last day she can get a seat on the cheaper flight. So I actually had to read this a couple times to kind of figure it out. The wording's tricky, but they're saying there's an amount of time when she can get a cheaper flight, and they're saying that she doesn't know if her exam is going to be here or after, right? So if the exam is scheduled here, she can't get the cheaper flight, right? So that's the idea. So we don't know when it's going to be scheduled, but they're saying the probability is 20% that it'll be here. There's going to be a 20% chance that the exam will happen after the last day. She can get a seat on the cheaper flight. So there's an 80% chance the exam will be somewhere in here. So basically all she has to do, so this is what kind of makes the question complicated, but if she just books her flight on that last day without knowing when the exam is going to be scheduled, then if the exam is scheduled any time before that moment, she's good. Any time after that moment, she's not, right? If the exam is after her flight, she has to cancel the flight. Okay, so here's what it says. She's going to go ahead with this, right? And it says if she has to cancel the flight, if this happens, then she'll lose $150. If she can take the cheaper flight, if the exam happens anywhere in here, then she'll save $100. So it's actually, there's not that much we have to do at the end, but kind of making sense out of this and understanding Mary's problem, actually, it took me a couple of reads. Okay, so anyway, part A is if she books the cheaper flight, what can she expect to gain on average? So we're talking about expected value of X, where X is Mary's gain. So we want to define the random variable. X is Mary's gain. Expected value of X is pretty simple, 80% times 100 plus 20% times negative 150. So I brought a calculator here. Guess these numbers aren't too bad. I could probably just do this without the calculator. But this turns into 80 plus negative 30, which equals 50. So on average, it's 50. Now, the funny thing about this is Mary probably doesn't care about the expected value because she's only going to do this once, right? It's not like she's going to do this 1,000 times and then on average she'll make $50, per flight. This is a one-shot deal, so she might very well lose 150 and gain 100. So expected value takes on kind of less meaning for her. But nevertheless, they ask us what is the standard deviation. So as we know, that's the square root of the variance of X. So first we're going to take the square root of the sum of each X value minus, right, you remember this. So, okay. So basically, we're going to do 100 minus that average squared times the probability of that plus negative 150 minus the average squared times the probability of that. And then we're going to add them and we're going to take a square root. So hang on, it's 50 squared times 0.8 plus negative 200 squared times 0.2. Square root of that is exactly 100. Okay, so that's all they wanted for that one. Okay, moving on to number 27. All right, number 27. Okay, now actually we've done 27. This is the batteries problem, but we'll run through it really quick again. We've got 10 batteries, 3 dead. We choose 2. So our random variable then is, of course, the number of good batteries out of 2. That's what we're interested in. So x could equal 0, 1, or 2. This is part A. They say make the model. And we want to know the probability of each one. So we say we're going to choose 2. This branching out is the first choice. This branching out is the second choice. So we have good, bad, good, bad, good, bad. And, okay, I'm still in my boundaries there. Okay, so we'll say probability of getting a good one, 7/10. Then if we chose another good one, that would only be 6 out of the 9 that remain. If we chose a bad one, that would be 3 out of the 9 that remain. If we're on this side, that means we're starting with 3 dead batteries out of 10. We chose one of those. To choose another dead battery out of the 9 would be 2 out of 9. To choose a good one, there are still 7 left out of the 9, so that's the probability there. We multiply down to get each probability of each elementary outcome. So that's, here would be, let's see, this would be 0.467. I'm going to go to the thousands place. Here would be 0.233. This would end up being the same probability here, 0.233, because it's another 3 and a 7 over 90. And then here I have essentially 6 over 90, which is 0.067. So here I have this probability for, well actually no, I'm getting this backwards. If I get 2 good batteries, that's the most likely thing. Or at least, that's the one right here. I'm not going to say most likely yet. 2 bad batteries is this one. That's x equals 0. Okay, and then for the middle, I have to combine these two, which, as I can see, is essentially going to be the same probability as this. Kind of amazing. It's basically the same. Okay, so part B is what's the expected number, and part C is standard deviation. So once again, we're finding this by doing this times this, plus this times this, plus this times this. So that's pretty quick. I get 1.4 out of that. See if you get the same. My variance of x is going to be, so I have 0 minus the average squared times 0.67. I have 1 minus the average squared times 0.466. I have 2 minus the average squared times 0.467. I'm going to add them up. So I'll do that really quick. Okay, I'm getting 0.374 as the total. So this is the square root of that. I'm getting 0.612. So I'm just basically rounding everything to thousands places. Hoping that's not too far from the accurate result. So these are my answers for parts A, B, and C here. Okay, moving on to number 29. Let's do 29. Did I have this one labeled? This is 27, good. 29, random variables. Okay, so they give us a table here for X and Y, and they say here's a mean and here's an SD, and it's 10, 20, 2, and 5. And they're saying these are independent random variables, and they want to know mean and standard deviation for each thing. So we'll keep the table going, basically. So we'll say if this is what we have, then for 3x, it's going to be 30, because all we have to do is multiply this by 3. And here, for the standard deviation of 3x, here's what we Basically, we just multiply by 3 again, but here's the reason. We would say the variance of x equals 4, right? Since the standard deviation is 2, the variance is the square of that, so I'll show that. Variance is this standard deviation squared, which is 2 squared, which is 4. Okay, there you go. Okay, so what we wind up with is 3 times the variance of 3x is going to be 3 squared times the variance of x. So that ends up being 9 times 4, which is 36. And then the standard deviation is just the square root of the variance. So I wind up with 6. So you might say, hey, wait a minute, all we had to do was multiply 3 by that. Well, yeah, because we squared to get variance, and then we took a square root again to get standard deviation back. You know, but it's good to go through that because you don't necessarily know. I mean, with statistics, you don't know what might happen, and you don't necessarily know. In a different problem, it might not be quite so convenient. So it's good to just make sure of yourself. That's what I'm doing. Okay, so here we have y plus 6. Okay, and then for the average, it's just going to be 20 plus 6. So that's simple. The standard deviation is going to be the same, 5. This doesn't change in this case because all we did was add onto the random variable. And all that means is that whatever this distribution is that has this distribution for y, it might look like this, but basically all that would happen would be just, it's just a shift. Like let's say the distribution's here and we add 6 and 6 is this far to the right. Basically we just moved the whole distribution there and that's all that happened. And so we didn't change how spread out it was, all we did was change where it was. So we didn't change the standard deviation. Okay, so now we'll do x plus y. Okay, so the rule here is the averages, they're going to add, right, to make 30. And then the standard deviations do not add. We don't get 7 here. But the variances do add. In other words, we might as well make another column here. Variance 4, variance 25, because it's the square of the standard deviation. These are going to add, right, down here to make 29. And then the standard deviation is going to be the square root of that. And so that's approximately, what, 5.4? What is it? No, not 5.4. Well, yeah, 5.4. Good. Okay. 5.4. Okay. So that's the way that works. Now, as for the next one, x minus y. So if you read, you're going to see, first of all, yes, we subtract these. But here, the variances simply add again. In other words, when we add or subtract x and y, the same thing happens to the spread. We don't subtract variances. It makes sense that the variation essentially increases the same way it does when we're adding, because essentially whether we're adding or subtracting, we're involving the variations of the variances of both variables to an equal degree. And we wind up with the same variance and therefore the same standard deviation. So variances don't subtract, they always add, even if the random variables are being subtracted. And then we have x sub 1 and x sub 2. Now that's interesting. Okay, give me a second here. All right, so what they mean by this is, what if we took one particular value of x, right, and another value of x, basically 2 instances of the same variable. We're going to sample 2 data points, let's say, from this set that x represents. Whatever it is, we don't even know what it represents, but let's say we're going to sample 2 data points. We expect, since they're on average equal to 10, we expect the sum of 2 particular x's to be 20, right? Well, just the same, now to do the standard deviation, we have to think the same way we were thinking here. In other words, here we added the variances, right, in order to get the standard deviation. Well, the same thing's going to happen here. We're adding 2 particular x's, we think of it as just two of these, which means the variance adds to itself. The variance of two x's added together is just 4 plus 4. Then when we take a square root, we get like that much. Okay? So again, this means 1x plus 1y. This means 1x plus another x, right? So it's as though it's basically just x plus x is what we're saying. They're put the subscripts down here to let us know we're talking about separate instances of the same random variable. Okay, so that's all of number 29. We're going on to 33. Okay, so number 33, an employer pays a mean salary for a 5-day work week of $1,250 with a standard deviation of 129. On the weekends, his salary expenses have a mean of, okay, so this is the week, and then we have weekend, or maybe I should just put E for end. Okay, is 450. So these are just tags. Like when I write this and I write that, those are just labels for you to differentiate. This is one average for one thing, and this is another average for another thing. So this is the average of the weekend, $450. So these are expenses actually. So hold on. It says here, okay, so standard deviation, expense, or sorry, weekend is 57. E stands for weekend. What is the mean and standard deviation of the total weekly salaries? Okay, all right, so hang on one second. Okay, so this is actually pretty simple. It's mostly just in the wording. Basically, we have our W, which is the total amount that he has to pay for the 5 days in the week. And we have the E, which is the total amount he has to pay for the 2 days in the weekend. And we want to know what is the combined. Like we want what is this and what is this, right? The combined average for the combined W and E and the combined standard deviation. So, so basically we're taking these and we're adding them together. So right now, maybe you're getting used to this by now. Yes, we add the averages. No, we do not add the standard deviations. What we add are the variances, right? We add the variances. And how do we get the variances? They are the squares of the standard deviations. So we have 129 squared, we have 57 squared, and this is what we get. So we can add the variances and get this. And then the standard deviation is the square root of that. Okay, so we got that, we got that. That's a quick question. This is what they wanted. Maybe I'll read it again just to make sure, but I'm pretty sure this is what they're asking for. Let's see. Yep, that's it. So this is all we need to know. Basically adding the averages and adding the variances and then taking a square root to get from here to here. And that's all we had to do for number 33. Okay. So finally in chapter 15, we have number 35 with the eggs. So we also did this already, or I don't know if we got to this in class actually, but okay, here's the way it works. Eggs. We got a dozen eggs, and in a dozen, so let's say that's a dozen right there, the mean, so this is going to be x equals number broken, okay? And the mean of x, and notice how sometimes when I talk about mean I use that, and sometimes I use that, but it's the same, right? So it's the same thing. So the mean of how many eggs I will find that are broken in this dozen is 0.6, so less than 1, which is good. It's still not great, but we're finding an average of 0.6 broken eggs Not 60% of the carton, just 60% of one egg, right? In other words, 0.6 eggs. Okay, and the standard deviation of X is 0.5 eggs. And we're going to buy 3 dozen. So we're getting 3 boxes here. And so that's really X1, X2, and X3. 3 particular X's. And we're going to add them together because we want to know in total how many broken eggs do we have. What do we expect? What's the standard deviation? So this is actually a lot like the last problem, right? It's just going to be, okay, so I expect this much in each one. So all the eggs, all the cartons, I should say, we add them together, we should expect 1.8 broken eggs. And the standard deviation, since it's 0.5 for one of them, the variance of X is going to be the square of that, which is 0.25. And we knew that without using the calculator. So if we add those up, we get variance of the total is the sum of the separates. So that's 3/4. And the square root of 3/4, if you remember your trigonometry, is 0.8, something? Well, it's like just like root 3 over 2. So if you 0.66, okay, 0.866. So it's like 0.87. Okay. So there we go. Now part C is important. It asks, what assumptions did we have to make about the eggs in order to answer the question? Well, basically, we had to assume that all this was independent, right? In other words, we had to assume that if we open this box, and let's say by some freak chance there are 3 eggs all broken in this box, which is way more than the average, right? We have to then say, well, that's okay, because now these 2 boxes also have an expected amount, which is 0.6, right? In other words, each one, no matter what, has the same probability of having, a few broken eggs, a lot of broken eggs. The probabilities are the same, so the expected value is going to be the same for all boxes, no matter what. Well, that's not really true in real life, because if this box has 3 broken eggs, right, that gives us some information. Like, actually, maybe that means that something weird happened, and if these boxes came from the same shipment, maybe that makes it more likely that these boxes would have broken eggs. I mean, who knows what happened, right? But in real life, as we get this kind of information, it does tend to change the probabilities, because in real life, almost nothing really is independent. So that's a big assumption on our part to actually treat the eggs this way and simply add the variances and add the expected values. Okay, we need to press on to chapter 16. So this is going to be, or no, 16? Yes, 16. Chapter 16, number 18. So going there now. Okay, so this is chapter 16, number 18. Arrows. An Olympic archer is able to hit the bullseye 80% of the time. Probability of success, 0.8. Okay, this is going to be binomial. Assume each shot is independent. If she shoots 6 arrows, so n equals 6, and I should also write here, since that's probability of success, I can just shorten that to p, right? This is the same thing as probability of success. So this is my n for my binomial model, and this is my p for my binomial model. Okay, so now what's the probability of each of the following results? So A, we want to know probability. First bullseye comes on the 3rd arrow. First success on the 3rd trial. Okay, well, we can just multiply. That's not failure, failure, success. That's what has to happen, right? The first time, 20%, next time, 20% chance. So basically, we're just multiplying those 3. And we get 0.032. Fine. Another one. She misses the bullseye at least once. Okay, so notice here there are 6 trials, but we didn't have to deal with them all. Basically, we just had to find out what we want to know about happens on trial 3, happens on trials 1, 2, and 3. So we just had to do that. Now we have probability that x, so we have to define x here. X is number of successes, right, in the 6 trials. How many successes? Probability that x, she misses at least once, which means she didn't hit them all. So this is the probability that x is less than 6. Okay, well, the easiest way to calculate this, we don't have to make the tree and everything. We can say, look, 100%, 1 is 100%, that's the probability that something happens, which something has to happen. We subtract the probability that she gets all 6, and we'll get the probability that she doesn't get all 6, right? Think about that. Either she has to get 6 bullseyes, or she has to get fewer than 6 bullseyes. There are no other possibilities, so therefore 100% minus the probability she gets all successes equals the probability that she doesn't get all successes, that she misses at least once, means the same thing. So basically we just do 1 minus 6 successes, and 6 successes is just 0.8 to the 6th power. So this is all we're doing for this one. And I have this if I round to the thousandths place. So it's quite likely that she will fail at least once. Okay. C, her first bullseye comes on the 4th or 5th arrow. So I could do first success on 4th or 5th. So I have to add those 2 probabilities. So it's going to be just like this one, we're just going to have to add 2 things. Okay, so 4th arrow would be this. 5th arrow would be this. And we'll just add those together. All right, so we're going to have okay, so this is not too likely. It's less than a 1% chance that it'll take her that long. Okay. She gets exactly 4 bullseyes. So x equals 4. So this would be probability of 4 bullseyes. So we have 4 successes. We have 2 failures, because remember there are 6 trials that we're talking about. And now we have to figure out the number of ways to get 4 successes out of 6. So we can go to Pascal's triangle to get this, or we can do 6 factorial over 4 factorial times 2. So I don't feel like writing out Pascal's triangle here. I'm just going to do, okay, so hold on. So this right here is 0.4096, this part. This right here is going to be, of course, 0.04. And then here I'm going to have, I'm just writing this out to remind you how it works. So here's my 6 factorial. Here's my 4 factorial. I also have 2 factorial. All this is multiplication. I can divide out all these common factors, and then I just have 30 divided by 2, which equals 15. So I have 15 here. This part is 15 times this times this. So that's all I'm doing. Okay, so I wind up with 0.2458. I guess I'll go to the 10,000ths place. I don't know why. Okay. So just going to shrink down what we have here a little bit so that we can keep going. Okay, part E, she gets at least 4 bullseyes. So this is going to be probability that at least, which means x is equal to 4, or it could be greater if we're saying at least. In other words, 5 bullseyes counts as at least 4, and 6 bullseyes counts as at least 4. So we already found this. So this really is going to be this plus, so we need to get the probability of 4, the probability of 5, and the probability of 6 and add them together. Well, you know what? We already found 2 of those. We found this one, which is that, and we basically found how to get this one, right? That's the probability of 6. So we just need probability of 5. So that's going to be, we'll do 0.8 to the 5th times 0.2 to the power 1 times the number of ways to get 6 out of 5, or 5 out of 6. Well, that's just going to be 6. And I know that from Pascal's triangle, as well as just what would happen if I simplified the 6 choose 5 calculations. So I'm going to do 0.8 to the 5th power times 0.2 times 6. And that's this. Okay, that's good enough. So now I'm just going to basically stack up. Probability of 4 is this. Probability of 5 out of the 6 trials is this. And probability of 6 is just like I did here, 0.8 to the 6th power. That gives me this. I add those up. Okay. And I get this. So this is what I was looking for all along. This is the probability that it was at least 4. Now the next question actually is no trouble, because the next question is basically, now that I've got this, they want to know that she gets at most 4 bullseyes. Okay, well, it's a little trouble. Basically, we're saying the probability that x equals 4 or is less, and that would be at most, right? In other words, if she got 3 bullseyes, if somebody said, did she get at most 4, we could say, yeah, she got 3. Did she get at most 4? Yeah, she got 2. She didn't get more than 4. So at most 4 means not more than. So it means less than or equal to. That's what at most means. Okay, so basically, here's what we could do. We could say, look, we know, this might seem tricky to you, but we could say, look, we know what the probability of, and I'll just write out the sample space here. I'll take more room. Okay, x is equal to the number of successes. So x could equal 0, 1, 2, 3, 4, 5, or 6. Now, this right here, greater than or equal to 4, counts as all of these, right? That's greater than or equal to 4. This one, hold on, I'm going to illustrate this with all the colors that I got. This one, less than or equal to 4, counts as all of these, right? So basically what I could do here, and just let me show you my thinking. What I could do here, I could take all of these and basically say, look, that's 100% minus the yellow. So I'll do 1 minus what I have here, right? This is the probability of 4, 5, and 6, and I already got that. I could take that away from 100% and get this. And then I could just add this on because I know what that is too. I figured that out here. So I have all these pieces. I just have to use them like I'm doing a puzzle. I could say, basically what I want to do is this equals 1 minus 100% minus 0.9011, which is this. That'll get me all of this. And then I just have to add on what I have here, and that's probability that x equals 4, which I calculated back here. Basically, so I don't have to go through a lot more, rigmarole here. So I'm going to do 1 minus 0.9011 plus 0.2458, and I have this. And I didn't write it very well. 0.3447. There you go. Okay, so I'm heading to the back of the book to make sure I got this right. Okay, well the back of the book doesn't have this answer, or at least not the version of the book that I have in front of me, so I'm moving on. But I'm pretty confident about all of this. Okay, so we're going to do chapter 16, number, 29 was the next one I wanted you to look at. Okay, so this is the tennis player also from exercise 25, and I see that her p-value for successful serve is 0.7. And she is going to serve 80 times, okay, which is a large number of trials. So what we're going to end up doing is using the normal model to approximate this distribution, okay. Part A is, what are the mean and standard deviation of the number of good first serves expected? So X is number of successes, right? Number of good first serve. So like we saw, mean and standard deviation are pretty simple. Mean is just NP, standard deviation is just square root of NPQ. So that's all we have to do. So it's just 0.7 times 80 and square root of 0.7 times 0.3 times 80. And so that just gives us 56. And it gives us 4.099. Okay, we'll do that. All right, now in part B it says verify that you can use a normal model to approximate the distribution of the number of good first serves. Now we're not going to get into, there's a process for making sure that we can use this to help us here, right? And we kind of talked about that. We said it has something to do with a sufficiently large number of trials. It also has something to do with P itself, right? But we're not going to get into that just yet. It will be important, and verifying what we call the assumptions and the conditions of a particular situation to make sure that we can actually do what we're about to do is going to be something that will be important, but we're just not going to deal with it yet. All right, so forget about part B for now, but we will be coming back to that. Part C, use the 68, 95, 99.7 rule to describe this distribution. So if I were going to do that, I would say the distribution, I would say 68% of the distribution. Or I wouldn't say the distribution. I'd put it even more in context. I'd say 68% of the time we'll see, you know what? I should really say approximately. Okay, so I'm getting into the AP language that's important here. Approximately 68% of the time, right, we're going to see out of 80 serves between, and now I got to do the average plus or minus the standard deviation. So I'll say 56 minus 4.099 and 56 plus 0.4099. And I'll say between 51.9 and 60.1 good serves. So I put it in context. I said approximately, which is important because I'm really approximating here. And I'm going to use the same language to keep going here. I'm going to say approximately 95% of the time we'll see out of 80 serves. So I'm just going to write the exact same thing between, okay, so now I'm going to do 56 plus 2 of these and 56 minus 2 of these. So this time, out of 80 serves, it's between this many and this many good serves, okay? and approximately, hold on, approximately 99.7%, it's going to be 56 plus 3 of these and 56 plus minus 3 of these. Okay, so I'm multiplying by 3, I'm adding, I'm subtracting. 43.7 and 68.3. Good serves. Okay, so we got through all that. Now, D, what is the probability she makes at least 65 first serves? So now we want to know, okay, so now we're really going to use the normal model, not just to make these really loose approximations, but something a little more specific. We're going to say the probability that X is, and it says at least, she makes at least 65 first serves. So X has to be greater than or equal to 65. So basically now we're talking about, and I'll make another model here, and I'm going to shrink this down even more because I really need some space to illustrate what I'm going to do. So now I'm going to say I've got a normal model. The middle of it is 65. No, it isn't. It's 56. I've got a particular value somewhere out here, which is 65, right? I want to know all this area. And the standard deviation is 4.099. So basically, I could find a z-score and do all that. And you know what? On the AP, why don't we do that? We'll say the z equals 65 minus 56 divided by the standard deviation, which equals, so do 56, so 65 minus 56 is 9, divided by 4.099, and I get 2.1, basically 2.20. So now I'm looking for the probability that z is greater than or equal to 2.20, which is not going to be a big probability. But we'll put this now in the calculator because the calculator, using the calculator now is basically equivalent to looking it up on the table. So I'm going to do normal CDF. I'm going to put in, since I already know my z-score, I'm just going to put in 2.2. So here's what I'm doing. Normal CDF 2.2 comma 1000. Okay, so basically I'm saying z can go from 2.2 to 1000. That'll cover the whole thing. And this is equal to 0.0139. There you go. Okay, that wraps up 29. All right, number 31, apples. Okay, an orchard owner knows it'll have to use about 6% of the apples he harvests for cider because they will have bruises or blemishes. He expects a tree to produce 300 apples. Okay, so a success, only 6% of the apples will go to cider. So that's for each apple, there's a 6% chance. He's going to get 300 apples. Wait a minute. No, each tree is going to be 300 apples. Okay, so I hope he has a lot of trees because that's not going to be a whole lot of cider. Okay, so a model for the number of apples for cider that would come from just the one tree. Okay, so, and it says describe an appropriate model. So we can describe the model by saying, okay, here's our variable. X is the number of cider apples from one tree. We'll say the model for X is approximately normal. This is how I would describe it. Model for X is approximately normal with a mean of, and I do the work somewhere out here or down here. I would say mean equals NP, which is 0.06 times 300, which is, and then what is it, 18? 300 times 0.06, 18. So you would write the work out. Same thing for this. You'd say standard deviation is this is okay, and what is that? 0.06, 0.94. Okay, 4.113, let's say. Okay, and so then I show this work. I write out the model for x is approximately normal. It's important to say approximately, with a mean of 18 and a standard deviation of 4.113. And that's your description of your model. That's good enough. It says justify your model, which means that we're also should be doing the whole checking the conditions and assumptions, but we'll get back to that. We'll talk about how to do that at another time. Find the probability there will be no more than a dozen cider apples. So now this is kind of like the last example. And we are going to find the probability that x is no more than 12. So that means less than or equal to 12. Okay, so once again, we've got a model here. Our middle is 18. We want, so 12 is over here somewhere, and we want this probability. So not likely to be 12 or less, it looks like. Okay, so that means we can do z equals 12 minus 18 over our standard deviation, which is negative 1.46, okay? And then we'll do normal CDF, negative 1,000, comma, negative 1.46, which is 0.072. Okay, so we got that. And then, is it likely there will be more than 50 cider apples? Okay, so we'll do the same thing for 50. Or it'll just, you know what, we don't even have to calculate the probability. They just said, is it likely? Well, we could just say, look, 50 is many standard deviations away from 18. That makes it unlikely, right? 50 is, we could just say, we could do that really quick. 50 minus 18 is 32. That's like, you know, between 7 and 8. 50 is between 7 and 8 standard deviations greater than the mean. Very unlikely. Okay. All right, so that takes care of 31. One question left, number 33. Wonderful, if you're still with me. Okay, now this is a great one. It's about the lecture hall with the left-handed seats. A lecture hall has 200 seats with folding arm tablets. So just imagine these seats, and they've got these tablets. This is like in college. And then when you sit down in it, the thing comes up and you can sit there and, you know, and it's really useful if you want to kind of go to sleep. Okay, now, it says the typical size of classes that meet there is 188, and we can assume that about 13% of students are left-handed, okay? So this is what we'll do. We'll say that a success is a lefty, a left-handed person, okay? And we'll say that X is the number of successes, so it's the number of lefties. Okay, and it says here that 13% of students are left-handed, so that gives us our p-value. P equals 0.13. Okay, typical size meets there is 188. So we'll call that our n. We'll say there are 188 chances to get a left-handed person. What's the probability that a right-handed student in one of these classes is forced to use a lefty arm tablet? In other words, what if they have, now it says right here, oh, and we missed, I might have read it too quickly, but there are 200 seats and 30 are for left-handed people, which means that 170 are for right-handed people. So maybe there are just not that many, left-handed people showing up. What if everybody's right-handed? Well, then that means some right-handed people have to sit in these seats. Okay, so they're saying, what's the probability that a right-handed student, at least one, that's really what that means. That doesn't mean exactly one. What's the probability that a right-handed student is forced to use a lefty arm tablet? We're talking about any scenario in which this happens, which means that the number of right-handed people in the room is greater than or equal to 170, right? If there are exactly 170 or fewer, nobody has to do that. So basically we're saying the probability, and so maybe we ought to switch this. Maybe for convenience we should say success is a righty. Why not? Success is an arbitrary idea, right? We can call success lefties, righties, whatever we want, but that changes the probability of success. Now it's not 0.13, it's 0.87, right? And Q is 13%. So Q is a failure. I hate to call lefties failures, they're not, but a left-handed person is considered a failure, and so that's a 13% chance. Right-handed person, 87% chance. This way we can define it this way, and it helps us to define it this way because now we can say we're looking for the probability that X, the number of righties, is less than, greater than 170, right? That's what we're looking for. If we have more than 170 righties, then one of them or more is going to have to sit in one of these seats. So now we're set. The whole thing is set up. We get the mean, which is just n times p. 188 times 0.87 equals 163.56. We get the standard deviation, which is 0.87 times 0.13 times 188, and then I take a square root and I get 4.611. Okay, and now I think about my distribution, which has a center at 163.56. I want to know, and here's 170, and I want to know the probability that we go beyond that. Okay, and it's interesting, well, I guess we did end up using the 188. Okay, so anyway, same old thing, z equals 170 minus the mean over the standard deviation, which equals 1.396, we'll say 1.40. So I'm going to do normal CDF from 1.4 to 1,000. And I get 0.0807, so I'll round to that. Is that the same thing I got before? No, it's not the same thing I got before. Okay, so here we are. And I think that's it, unless they have something else to ask us. Nope, that's it for 33. Good job if you hung on with me the entire time. Wow, it's almost an hour. Okay, well, look over these, rewind, fast forward, slow-mo, whatever you need. Study, study, study. And make sure you understand these. And I'll see you guys really soon.